In this lesson, we are going to discuss one of the most basic integration techniques called integration via substitution or just substitution. And by the end of this lesson, you should be able to apply substitution to both indefinite and definite integrals and use linear substitution patterns efficiently, but we'll get there. Don't worry about using anything efficiently yet. First, let's introduce the technique called substitution. And previously, we have established the fact that the definite integration heavily relies on indefinite integration. And when it comes to finding antiderivatives, we only had really two options available to us, either to recognize the integrand as one of the functions whose antiderivative are well known, or the second option was to manipulate algebraically or symbolically the integrand into a linear combination of functions whose antiderivatives are well known. And this was due to the fact that we only used the following properties of indefinite integrals that we acquired from directly translating the properties of derivatives. So we know that finding an antiderivative is the opposite of finding the derivative, and naturally integration inherits the properties of differentiation when it comes to things such as linearity, meaning integral of a linear combination is a linear combination of integrals because derivative of a linear combination of functions was a linear combination of derivatives. However, these are not the only properties of derivatives that can be used and flipped around. We also, I don't know if I'll be able to edit here, but we also, nope, didn't work. We also can use the chain rule and flip the chain rule around. And this is something to note. The substitution technique is based on the reversing the chain rule property of differentiation. In the future, not so distant, you will also learn how to undo the product rule, and that process will be called integration by parts. But integration by parts is not a basic. When you learn it, it will become basic, but at this point, we're not going to consider it as one of the basic integration techniques. This lesson focuses entirely on the integration by substitution. So let's see how it works by considering the following example. I'm going to write the answer here. I mean, not the answer. I'll write the question here, and let's see if we can catch that pattern. So what's the integral of this function equal to? Whatever it is, whatever we're going to write here, it's going to be because when we take this and integrate, or rather differentiate, we're going to get 3x squared e to the power x cubed. So can you guess derivative of what function is equal to 3x squared e to the power x cubed? And the answer is, we can guess, but we can also kind of see the pattern here. What is the pattern? We have derivative of x cubed, and we have e to the power x cubed in the integrand. So that means it is clearly the pattern of chain rule. So the general antiderivative of this function is e to the power x cubed plus c. Why? Because derivative of e to the power x cubed is going to be e to the power x cubed times 3x squared by the chain rule. Now pause the video and find this antiderivative using the pattern that we just discussed. What would this be equal to? I'll give you the answer in 3, 2, 1. So the antiderivative of this function is going to be sine of x cubed. How do I know that? because derivative of sine of x cubed will be equal to cosine of x cubed times the derivative of x cubed by the chain rule, which is 3x squared. Similarly, let's do the next problem. So we're going to spend the whole lesson doing this, so you need to be good at the applying the chain rule for sure. We'll do this example first, and what do you think the answer is? This becomes less trivial, but if you remember that derivative of 1 over square root of 1 or plus x squared, if you remember what the derivative of this function is, which is going to be 1 over 2 square root of 1 plus x squared times, by the chain rule, 2x, then you should be able to see how, and it may help to add these 2's over here. You see that this is the derivative of a function, some function, and this is the derivative of the input of this function. So the answer would be 1 over square root of 1 plus x squared plus c. Now try this. And if you're worried about whether you'll be able to recognize these patterns, don't worry about it yet. We're definitely going to make this process more efficient. Let's find the antiderivative of this function. I'll give you the answer in 3, 2, 1. So the pattern is that if you differentiate 4 plus x squared to the power 3 halves, what will you get? You'll get 3 halves 4 plus x squared to the power 1 half times the derivative of 4 plus x squared, which is 2x. And then 2's will cancel, and you end up with exactly that. So antiderivative of this is 4 plus x squared to the power 3 halves plus c. Let's do... Let's turn this into a procedure rather than guess and check. To turn it into procedure, we're going to follow these steps. I'm going to copy and paste it here, and then we follow these steps on some example. So let's say let's do another example. Let's do integral of tangent x secant squared x dx. And let's follow this procedure. So the first step is says within the integrand, look carefully for an expression g of x such that the derivative part of g prime of x, sorry, not the derivative, the variable part of g prime of x. What does that mean? That means we don't really care about the constants. Constants can always be brought in and out of the integral, so we only care about the variable part. And we want the variable part of the derivative of g to be a factor of the integrand. So let's look at this integrand carefully, and let's try to find a function whose a function of a function, and the derivative of the input function of the inner function is present as a factor. In this case, we can totally, it's impossible not to remember that derivative of tangent is secant squared. So it looks like we did find a function whose variable part of the derivative is also a factor. So such function is tangent x. And next we introduce a new function called, let's use letter t. So it's a function slash variable. On the one hand it's a variable, on the other hand it's a function. Right now we treat it as a function, but later we're going to be treating it as a variable. But t here is going to stand for tangent. So we're going to refer to tangent moving forward as t. So that immediately takes care of this part of the integrand. So this is t. Now replace, sorry, we're not done yet. So introduce a function and find dt. So dt is a differential. Differential is equal to the derivative times dx. So it's going to be derivative of tangent, which is secant squared x dx. And now notice how this is kind of what triggered the whole substitution, and this is dt. Now in step 3 it says replace g of x in the integrand. So we're going to write the integral and replace g of x. So replace tangent x with t and g prime of x dx with dt. So when you do that, you literally end up with nothing but a function of t. So now we're going to be treating t as a variable, and if you treat t as a variable, you see how this integral is pretty easy. It's just an antiderivative of t, which we know is equal to 1/2 of t squared plus c. Now, we found the antiderivative in terms of t, and now we're going to plug in g of x back into this function. So the answer shouldn't have t in it, the answer should be in terms of x, because that's how the original question was asked. So in the last step we plug in tangent x for t. No, dx. Got carried away here. Plus c. And now that the final answer is in terms of x only, we are done. Now, when you organizing your work, what I suggest is isolate this substitution computations and substitution, like all the things that you do relative to substitution, like isolate it and label it carefully with the word substitution. This is crucial because later you will learn integration by parts technique, and it to an untrained eye, integration by parts and substitution may look the same. So clearly label what you're doing. So if you're doing substitution, write down substitution. If you're doing integration by parts, write down integration by parts. But this is what a complete solution looks like. Well, I've done this one. Now I want to ask you to try a similar problem. Doesn't have to be similar, but I want you to try a problem. And the problem that you're going to try is the integral of tangent squared times secant x dx. So you may say like, well, it's pretty much the same problem, but it's not. So take a look at this problem, pause the video, poke around, and I'll give you the answer in 3 seconds. 3, 2, 1. So here, before we actually do substitution, we have to recognize the pattern. And the pattern in this problem is not that obvious. So to see it, we're going to split that tangent squared into tangent x and tangent x secant x. Hold on. Secant x. Am I hold on, I'm tripping. This is not helpful at all because derivative of secant. So what I actually wanted to do, forget about this problem, actually, no wonder. So if you spend more than an hour thinking about this before you unpause the video, that's okay, because this was not an easy problem. Let's instead do this same problem in a different way. So let's recognize a different pattern here. So instead of tangent x, we're gonna write it like this. We're gonna write secant x, and then we're gonna write tangent x, and then another secant x dx. And how is this helpful? Because now I'm actually going to recognize this as my g prime of x dx, and this is going to be my g of x. And my substitution will be organized in the following way. T is equal to secant x, dt is equal to tangent x secant x dx. And now I'm going to plug everything in. And we have the following. So the secant x now becomes t. The tangent secant x becomes dt. And I end up with the same antiderivative, which is 1/2 t squared plus c. And we're going to replace t with secant x. Now you might wonder, how's that the same problem has two different answers? We addressed that concern in one of the previous lessons when we discussed the antiderivatives and indefinite integrals. So there's nothing wrong with that, so we solved the problem. All right, let's continue doing the same things, but without that process written in front of us. Let's do integral of cotangent x. Same thing, the pattern may not be obvious, but you may have to rewrite your integrand to see the pattern. And now we're going to do substitution. So t is going to be equal to sine of x, and cosine of x will be my dt, part of dt. So this now becomes 1/t, and this becomes dt. And this allows for an effective substitution. So we have integral of 1/t dt, which is ln of absolute value of t, plus c, and then replace t with what t stands for, and this is the general antiderivative. Next, I want you to use the same example or template and integrate the tangent of x dx. And I'll give you the answer in 3 seconds. So pause the video if you want to work on it by yourself. 3, 2, 1. So unpacking this, we have 1/cosine x. Here we have sine of x dx. You might say like, well, if you make this substitution, t is equal to cosine x, you have dt equal to negative sine x dx, but there is no negative here. So what do? Well, there are two ways. Like, either you move that negative there algebraically and then you put another negative here. That's one way. And you're going to then end up with the integral of negative 1/t dt. Or what you can do is you can acknowledge that you don't have negative sine x dx, you have sine of x dx, and you can move the negative here. So it's negative 1 dt that is equal to sine of x dx. And then when you plug everything in, you're going to end up with integral of 1/t times negative 1 dt. Either way, you're going to end up with that negative there, and the final answer will be the same. So it's negative ln absolute value of t plus c, negative ln absolute value of cosine x plus c. All right, let's continue. Let's do this example. Let's integrate x over square root of 1 plus x squared dx. So I think we previously were able to guess that antiderivative, right? Somewhere here. Did we? Somewhere here? Is that it? Yeah. Right. So, but as I said at that point, I said, well, if you feel like guessing is hard, the good news is like you don't have to rely on guessing. But you do need to learn the procedure and actually be able to execute this procedure. And by doing that, like, eliminate the need to rely on recognition of the pattern. So here, what do? We are going to do the substitution. And what are we going to substitute? The rule of thumb is that we substitute things that like causing us trouble in finding the antiderivative. So I'm like, I can barely wrap my mind around radicals, but like radicals of something else, it's like, that makes it even harder. So whatever that something else that makes things harder, you can call it a new name. So in this case, we can just say, well, 1 plus x squared is hard. Let's call it t. And then dt will be equal to 2x dx. And then same thing, like, because I see how I don't have 2x dx, I'm going to push this a bit further and write x dx as 1/2 of dt. And now I'm going to substitute everything in. So instead of x dx, I'm going to write 1/2 dt. And in the denominator, instead of square root of 1x squared, I'm going to write square root of t. And do you see how every instance of x got eliminated, and we have nothing but the integrand in terms of t? That means you've made a successful substitution. Now we just need to focus on integrating this function. And this is just square root of t plus c. And square root of t is not really square root of t, but square root of 1 plus x squared plus c. Make sure you're not making a mistake of integrating a function in terms of t when differential is still in terms of x. Another mistake students make frequently is they don't put dx or dt anywhere, and then when you're doing substitution, it makes it really confusing. Have you done the substitution? Have you considered replacing dx with some function times dt, or you just forgot about it all? So make sure you write your differentials. It's not just a formal part of the notation. In techniques like substitution, we heavily rely on what comes after that d. Are we still integrating with respect to x, or we're already integrating with respect to dt? That matters. Now I want you to try one on your own. So try this problem. Using the same substitution, I'll give you a hint. So integrate 3x square root of 4 plus x squared dx. The hint is t equals to 4 plus x squared. So go ahead and try that. And I'll tell you the answer in 3 seconds. 3, 2, 1. So if the substitution suggestion is there, you just have to kind of follow that trail to the end. Dt is equal to 2x dx, and the substitution then looks like this. We have, what do we have here? So we want to kind of rewrite this as 4 plus x squared times x dx. 3 can be written outside, and then we can throw this 2 over here and take it out over here, or instead of x dx, we can just write 1/2 of dt. Either way, you'll end up with the same answer, so let's not worry about it. What's more important is that we can plug everything in. 3 times square root of t times 1/2 dt. It's now a much simpler integral. And the final answer is t to the power 3/2 over 3/2. 3/2 cancelled. But instead of t, we have to write what t stands for. So 4 plus x squared to the power 3/2 plus c. Now, I want to make a few remarks now that we have practiced this a few times. In this process, and I'll copy this process here again. So let me bring this over. In this process, sometimes in step 3, we may need to express x in terms of t by actually writing x as the inverse of g function. And then rewrite dx in terms of dt explicitly instead of looking for that pattern to replace dx with something else, with dt. So you definitely have to make a note of this, or remember this note when you're trying to do substitution and x's and t's just don't cancel. So you try to eliminate x, but x is still lurking around in the integrand. So remember of this note. That means you may have to do a bit of extra work to get rid of x. That, or maybe that wasn't a good substitution altogether. So those are kind of the two diagnostic suggestions that I have. Now, another suggestion is that by now, by probably Googling or ChatGPTing this topic, you have seen that many traditional textbooks or many mainstream textbooks, and therefore ChatGPT, refers to the substitution technique as U substitution technique, which is ridiculous because later we're going to learn a new integration technique called integration by parts, and the same mainstream books but use letters U and V to set up the integration by parts. So when you're using the same letter for two different techniques, it creates the confusion and takes away the clarity. In this class, we consciously going not to use letter U for substitutions, but use letter T instead. So if I see anyone on the exam using letter U, I'm not going to be pleased by the fact that you're not learning from me, but trying to learn from ChatGPT. But the bigger problem will arise when you get to the next calculus class, and you're going to be using both procedures to solve the same integral, and you're going to be forced to kind of pick whether to use a different letter for your substitution or try to use different letters for your integration by parts, because traditionally both of them use letter U, according to some textbooks. Again, in this class, we're going to keep using letter T for our substitutions, and we're going to refer to this not U substitution, but integration via A substitution. It doesn't have to be U substitution. There's nothing really special about letter U. So let's make these two notes, and let's move on. Let's continue practicing this skill. So the next problem is going to be something. What did we do last? We did this. So next problem, let's do this one. Let's integrate this. It becomes less and less obvious what the pattern is. So, but the rule of thumb is just substitute whatever kind of is on your way to find the integral. And substituting something inside of the radical, it's a common strategy. So we're going to do substitution, and we're going to replace t with square root of 1 plus x squared. Or the other way around. We're going to replace square root of 1 plus x squared with t. Actually, not the whole radical. Just what's inside of the radical. 1 plus x squared. And then dt will be 2x dx. And if you try to plug everything in now, you're going to see how, well, there's nothing there to substitute x cubed, right? We do have square root of t in the denominator now. And dx, like, there's no, sure, we can split up x from here, but like, in general, we don't really know what to put here instead of dx. So when you run into an issue like this, you just things don't cancel. Consider doing this. Solve for x. So turn this into, first, x squared equals t minus 1, and then x equals square root of t minus 1, and turn this into, first, 1/2 of dt equals x dx. That could be helpful. Or, if that's not helpful, you can turn this into 1/2x dt equals dx. And now substitution becomes kind of more straightforward. So instead of x cubed, I'm going to write, well, because I don't have anything for x cubed, but I do have x, so I'm going to write, or in the meantime, you can still write it as x cubed, right? That's not the goal. Like, you can substitute everything in stages. So let's write x cubed as x cubed. In the denominator, we're going to write square root of t. And now instead of dx, I'm going to write 1 over 2x dt. The goal is to get rid of all the x's. I cannot get rid of all the x's. After I reduce this x, I still have 1x, or rather 2x's left over here. So we still have x squared. But now you look into your substitution section and you look that, well, x squared could actually be expressed as t minus 1. And that kind of completes the substitution. So we're doing all of this in the spirit of this note. Remember, sometimes you may need to do more work in your substitution section, and when that's necessary, you gotta be able to recognize that need. And now we have a simple, or rather simpler integral. We do it by dividing square root of t into t and then 1. So we still have an integral. We haven't found the integral yet, and now we're about to find it. So we're going to have 1/2 t to the power 3/2 over 3/2 minus t to the power 1/2 over 1/2 plus c, and this is the final answer after simplifying everything out. We now need to replace t with what t stands for in terms of x, and now we are done. There you go. Your final answer must be in terms of c. Alright, let's do another problem. This time it's your turn. I'm not going to... Actually, no, well, we have to pick our battles, I guess. You can always check your work with ChatGPT. Just make sure your ChatGPT set the criterion for good solution to be having a substitution section in which t and dt and x dx are explicitly written in terms of one another, and I'll show you right now. But pause the video and solve this problem, and in 3 seconds I'll tell you the answer. And the answer is 3, 2, 1. So the final answer should be, according to my calculations, should be 3/5 4 plus x squared to the power 5/2 minus 4 plus x squared to the power 3/2 plus c. And that was done using the substitution t equals 4 plus x squared. Check your work. However, what I wanted you to let your AI know, that when it show you the solutions for this type of problems, it has to follow this template. All applications of substitution for finding indefinite integrals should look like this. You have an integral, you have a substitution section in which you tell me what your t is in terms of x, what dt in terms of dx. When necessary, I also want to see what x is in terms of t and what is dx in terms of dt. And then you plug everything in. Hopefully you get rid of x. If not, then more work needs to be done here. When you get rid of everything in terms of x, you have a function of t. Hopefully you'll know antiderivative of that function, and then don't forget to plug in g of x into the final answer, as your final answer has to be in terms of x. So let your ChatGPT know that these are the explicit steps that you want to see, and then ChatGPT is probably not that bad, and it can perform substitution probably faster than any of us can. So you can use it to help yourself studying substitution. All right, let's move on. Oh, let's do one more example, I guess. Hold on, let me see. let's move on. But definitely, there shouldn't be a time where you say, I've done too many of these substitutions. No, like, keep on doing them, and after you're done, keep doing more of them. All right. Now, once the substitution technique is mastered for indefinite integrals, there is no really additional skill needed to apply it with definite integrals. So, for example, if you trying to integrate dx, this is sloppy notation, 1 over x square root of ln x dx, and you're trying to do definite integral and integrate this from e to the 4, you can kind of hit the pause button here and say like, well, let's first find the antiderivative of this function, right? And then you do your substitution here. So this is substitution. What's the substitution? T is equal to ln x, dt is equal to 1 over x dx, and then this integral now becomes 1 over square root of t dt. It becomes 2 square root of t plus c, and it becomes 2 square root of ln x plus c. So you can do that. And when you find the antiderivative using substitution, you can then kind of unpause your solution. You can hit like the play button for your main solution, and you can say like, well, now that I know the antiderivative, the general antiderivative, I can use the fundamental theorem of calculus part 2 to write it like this. And then you just plug everything in. And then the answer would be 2 square root of 4 minus 2 square root of 1. 4 minus 2 equals 2. So as I said, no special skill is needed. However, we can definitely streamline the integration process, and instead of hitting the pause button, we can just say, well, let's integrate it. Let's embed the substitution into the definite integration process. What is it going to look like? Well, there are two ways. First one is to do it this way. So we say we're going to do substitution. Substitution is the same. T is equal to ln x, dt is equal to 1 over x dx. So we have this integral now. It's 1 over, it's 1 over square root of t dt. And remember, we had a definite integral. So it could be very tempting to put e to the 4 here. But that's wrong, because e and e to the 4 are the limits of integration with respect to x. Now that you have a new variable, you don't know what your limits of integration are. And because you don't know what they are, the least you can do is not to put the wrong ones there. So one thing you can do is you can just put some values here. So you can say like, hey, I don't know what they are. I don't care. The only reason I'm writing this is so I can find the antiderivative. So let me just put some a and b as placeholders, and let's continue the integration process. You then find the antiderivative of that. It's going to be 2 square root of t. And now we want to start using the fundamental theorem of calculus, but you cannot, because a and b are unknown. But the good news is that if you go back to x, so if you start writing ln x instead of t again, now you can continue with the application of the fundamental theorem of calculus, and now it makes sense. So we can write this as ln of e to the 4 minus 2 square root of ln of e. And you see how you're kind of back on the same track as here. Like, this is where we're at right now. So of course the answer will be the same. So the answer, the final answer is 2. However, this is not the only way of embedding substitution in the definite integration process. Let me show you the other way. So back to this problem. back to this problem. Actually, this is all good. Up to here, it's all good. It's all good. It's all good right here, right? And we know we're about to write the definite integral in terms of dt. And previously we said, well, I don't know what these limits of integration are. Oopsie. So let's just write a, b. But why don't we just find what these limits of integration are by doing this simple conversion. And fill out this table. So here we're going to put the limits for x. So the limits for x are e to the 4. And here we put the limits for t. So if x is e and t is equal to ln x, then what would be the limit, the lower limit with respect to t? It will be ln of e, which is 1. And ln of e to the 4 will be 4. So these are your limits of integration with respect to t. So with respect to t, we're going to integrate from 1 to 4. What function? The function is the same. It's going to be 1 over square root of t dt. And when you do that, this is what it looks like. We find the antiderivative, and now we apply the fundamental theorem of calculus. If in the past we could not do it until we plugged in x back into the antiderivative, now we can do it because we have limits of integration with respect to t. So we finish the solution by doing this math, but you can see how we're literally jumping on the same track as before, except we're kind of bypassing certain steps. I like to say we are front-loading certain computations. So in this technique, we kind of front-loading these computations into here, and the math is going to be literally the same. If you look at this side by side, it just looks, the way we write the solution looks slightly different. So keep in mind that some people don't like substituting. Sometimes you must substitute, so it's better to know how to write your solution this way rather than rely on just this way. But again, when someone else writes their solution in a slightly different way, don't get all confused. However, speaking of ChatGPT, make sure your ChatGPT tells you the answer the way you want to see it. So you can instruct ChatGPT to give you the answer with substituting the limits of integration as a part of substitution. All right. All definite integrals. So depending on which path you're going to take, now either going to look like this when you apply the substitution. So this is like your template to feed into ChatGPT, or like this. So these are your two alternatives when it comes to using substitution for integrating definite integrals right here. So this is 1 when you don't change your limits, and this is 2 when you do change your limits. But the math is going to end up being exactly the same. So it's just, they are just visually different. All right. Let's see. The easiest substitution of all, well, I guess maybe I should give you like a small practice, something simple. So go ahead and integrate this from 0 to pi over 2. And press the pause button, but in 3 seconds I'll tell you the answer. So 3, 2, 1. We're going to do substitution. So we're going to replace t with sine of x. And in this case, like, I just want to, you don't need to be attached to letter t. We can use letter s to represent sine of x. You can use letter l to represent logarithm, or some capital E to represent like exponential function. But let's use letter s to represent the sine. ds then will be cosine of x dx. And we can substitute everything in, and we're going to end up with s ds, and we are near the finish line here, right? As long as we know the limits of integration. So let's do the change of limits right here. So when x is 0, what is t or s is equal to? Well, s is going to be equal to sine of 0, which is 0. And when x is equal to pi over 2, what is sine of pi over 2? 1. So now we know the new limits of integration from 0 to 1. We can finish this problem. So the final answer is 1/2. All right, let's move on. So the easiest substitution to perform is a linear one. What is a linear substitution? A linear substitution is when you have a function of some linear function. So a composition of a function with a linear function. So an example would be something like this. Let's do integral of sine of 3x minus 1. So what do we do here? Well, we do substitution. What substitution? Well, we need to substitute that 3x minus 1. So we set t equal to 3x minus 1. dt will be equal to 3 dx. Dx will be 1/3 of dt. We can write it here. And then when you substitute everything in, you're going to end up with integral of sine of t dt, and 1/3 is right there. So we have 1/3 integral of sine of t dt. The answer is going to be negative cosine t plus c, and negative goes out, and instead of t we'll write 3x minus 1 plus c. So the idea is that if you compare what we just got with what we would have gotten if there was no 3x minus 1 here, right? So what if this was just sine of x? Then we wouldn't need to do any of this, right? We would have just written what? We would have written negative cosine of x plus c. But when we have sine of 3x, what was it, minus 1 dx, what did we do? We wrote negative cosine of 3x minus 1 plus c, and we also had like that 1/3 in the front. So the point is, when you looking at a problem like this and you compare it with this simple fact, that's not much of a leap to conclude that this integral must be equal to this. So we call this a linear substitution. And linear substitution, you can certainly write it out step by step, and there's nothing wrong with that. So if you are actually confused by what's going on, you definitely want to write it out step by step. But the point is, eventually, after you write this step by step down like 15 times, you'll be like, man, this is annoying actually. Can I just skip the steps? And the answer is yes. It's not that hard to just skip literally the whole thing and just jump from the actual problem to recognizing that it's a linear substitution and just write the answer like this. It's not that hard. So that means what? That means if I ask you now to, let's say, hey, go ahead and try integrating cosine of 3x minus 1. Well, you know the answer is going to be sine of 3x minus 1, but the way these constants play out, we have to divide by whatever the multiple of x is there. So it's going to be 1/3 of sine of 3x minus 1 plus c. It's that easy. So if I ask you now to, let's say, I'm going to ask you, I'm going to do it myself. Let's integrate 2x minus 1 or plus 1 to the power 3 dx. Well, if this was just x, the answer would be what? X to the power 4 divided by 4. But it's not x, it's 2x plus 1. So this linear substitution would work out exactly the same way. It's going to be 2x plus 1 to the power 4 over 4. 1/2 goes in the front, plus c. Now you try. Go ahead and try, let's say, integrating e to the power 7x minus 5. What do you think the answer will be? Well, in 3, 2, 1. 3, 2, 1. The answer is e to the power 7x minus 5 times 1/7 plus c. This is called the efficient way of doing linear substitution. If you do have to write it out, then you have to follow these steps and write it out completely. But if you're not, but it's completely within your reach to just practice it to the point where you're like, oh, that's a linear substitution, here's the answer. Now, you still gotta be careful, right? So just because you've seen how someone else does it doesn't mean you can do it immediately and correctly all the time. So you gotta be careful with when we have a fraction there. So for example, if we have the integral of 1 over x over 2 plus 3 dx, I want to treat this as t. So the answer will be ln of t, which is x over 2 plus 3. But now here I'm going to write 1 over what? So it's going to be 1 over the coefficient of x. But coefficient of x is 1/2, so you got to be careful. It's going to be the reciprocal of 1/2. And we usually don't write the reciprocal of a fraction. We just flip it and write 2 in there. So go ahead and try making this transformation yourself. So let's integrate e to the power x over 2 plus 3. What do you think the answer will be? In 3, 2, 1, the answer is e to the power x over 2 plus 3 and 2 in the front plus c. Another common mistake, not a mistake, but like negligence, I guess. Students forget to interpret the negative sign correctly. So for example, if we have integral of 2 over 3 minus 5x squared, what do I do? Dx. What do we do? We interpret 3 minus 5x. We're going to treat it as t. So the answer then will be negative 2 over 3 minus 5x. And now we need to, well, so the negative comes from the antiderivative, right? And now we have to multiply it by the reciprocal of what? Of 5, or negative 5, which is what? Negative 1/5. So you still have to be careful there, but the point is, once you master it, this is super fast. Like, it's just, you don't want to spend more than like 10 seconds doing linear substitution. Now you tried something also non-trivial, secant of pi x over 2 tangent. Oh, I guess if we want to practice negative, let's do negative. Let's just do integral of e to the power negative x over 2 dx. What would be the answer? The answer will be, in 3, 2, 1, e to the power negative x over 2 divided by the coefficient of x, which is negative 1/2. So reciprocal of negative 1/2 is negative 2 plus c. So this is, again, what we called linear substitution. And one of the objectives was, at the beginning, using linear substitution patterns efficiently. This is an efficient way of using linear substitution pattern. Now, as you have seen in this lesson, substitution is a powerful tool. We're about to finish this lesson, which unlocks a whole new range of integrals. In a similar way, the chain rule unlocked a whole new range of derivatives for us earlier in this course. To use substitution means to transform the complicated integrand, and by identifying patterns, into the integrand that consists only of one other variable, and the integrand must be simpler than the original integrand. So that's what it means to perform a successful substitution. Now it's time for you to practice. Only with experience you will develop this intuition for when and how to use this technique efficiently and properly. So we're going to end the lecture here. If you have any questions, feel free to reach out.